Am I live? Is that okay? I upgraded OBS, and it usually has a little button that says "Go live." Now it says nothing. It just says auto stop. So I guess I've been live for a couple seconds now. Sorry, a minute of dead air there. Okay, well, let me just verify that. I want to double check that I'm actually. Like everything was gone on YouTube here. On OBS when I upgraded, so like everything is different. Like the whole layout of the thing changed. Everything is just screwed up. So let me just double check. So I'm just where would I be? YouTube? I don't know my own channel. At Tangent Stream, right? YouTube.com/@tangent. And it says I'm live, so okay, sorry about that. Sorry for the dead air. All right, well, what we're doing here, as it says, still verifying rake.lean. So let's move into this. So I broke some stuff. I've got a month left to make this video, and the video that I want to make about this project, and I'm not done with the proving. I thought this would take a short amount of time, and it's taken weeks now. But that's okay. I'm learning, and you know, I think it started out as like 10 lines of code. You know, the Daniel's original thing is like 4 lines of J, I think, and you know, I made it a little more extravagant with this whole notion of arithmetic sequences that were an object type. And anyway, but it was a short amount of code, and it's just taken me forever to prove it. I had to come up with this whole theory of like what is a prime sieve, and how does that relate to just a generic prime generator, and then you know, then I had this implementation of it. So the general logic is done. Like this is all proven. We have a basic theory of what a prime sieve is, how it works, and if you can create something that has certain properties, then you can prove that it is a prime sieve, and it will the prime sieve class will provide you with some proofs that you need in order to show that the things that you're generating actually are the consecutive primes. So what you have to prove, or what I have, you know, on this side of the fence, what I have to prove is basically these statements at the bottom of this file, that at every step, you know, you have to prove this, that there's you always have some prime that you're looking at, you always have a candidate for the next prime, and then you have some way of modeling the sets, the set of all the primes that are all the numbers that are not divisible by the primes that you've already crossed off, basically. So all the primes less than that p are all so the property is for all natural numbers. The property n is the same as n is a member of R of p. So R is defined in the prime sieve file, and it just means the set of all natural numbers greater than or equal to 2, such that if that for all q less than the some natural number p, if q is prime, q does not divide n. So basically, any number less than p are the numbers that are the primes that we've identified, and that we've crossed them out. We've crossed out all the multiples, basically, and that leaves R as the set of all the numbers that are left. And if we can prove that this C is the minimum of R, so a C is in R, and everything else in R is less than or equal to, I'm sorry, rather C is less than or equal to everything else inside of that set, then it is the minimum, and that is the next prime, right? So we prove this much, and then the prime sieve does the rest of the work. So that's all well and good. That's how it. Hang on. What is it telling me? Oh, my bit rate is too slow, and we recommend that you stream at a bit rate of 6,800 kbps. Well, I cannot do that because I can do nothing more than what I have now. Can't get out and push to make the internet go faster. All right, so sorry if this stream is somewhat fuzzy or whatever. Anyway, so what I've done in the past couple of days when I have not been on camera is I've been, I think the last time I had gotten it down to this file rake. Yeah, that's why I'm looking at rake.lean in the name of the video. And I made a couple changes. Primarily, I think I might have been starting this in the last video, but basically I replaced the structure I originally had, which was I had a collection of these arithmetic sequences. I made a new type. So aseq was an arithmetic sequence. It's k plus d times n. So you just track the k and the d, so it's just two numbers. And then you have all these functions associated with it and some proofs associated with it. And I created a new type called dseq that was like a collection of these that all have the same d, same delta, the same slope of the lines, right? So these are arithmetic sequences. They're just lines, but you're looking at the points where they intersect the integers. Every input is an integer, every output is an integer, and you get a sequence of discrete numbers. And so then my data structure, a rake, is a collection of these things. So it's a rake because it's a bunch of parallel lines, as if you were dragging your rake through the sand, right? So I call it a rake. And I had this structure called dseq, and it was causing me to. It was just complicating the proofs quite a bit. Anytime, basically, I was baking that letter D into the type, so that the type of it was an arithmetic sequence. It was a subtype of arithmetic sequence where D was a particular number, and then there was one of those subtypes for every single possible number D. And then that way, on the rake, I said, well, I have D is a natural number, and then I had a list of sequences. That were arithmetic sequences that shared the same letter, but now what I have instead is a list of constants, and so they're just that k term for each one. And what I do is I construct the arithmetic sequence on the fly. So when I need to do something, I go through and I look at all the k's, and I map some function like this one that actually generates the sequence for me and then does some operation. And then also previously what I had a bunch of, I had these two proofs associated with every instance of the type. So h size is this notion that there are some that there's at least one k, there's at least one constant, so there's at least one sequence in the rake, and so you had to prove that for every step. And you still do, but at least now you don't have to explicitly state it for these like simple ones right here. Like you can just, I added this little tiny bit here that automatically provides that proof. And in fact, and then I also have a sorted proof. And what I did, I think yesterday, is I extracted this sort command. So rather than making so you notice it says there's now two things, right? So there's sorted is a Boolean that's just like a piece of data associated with it. So you can set that flag to true or false. And if it is true, then this is an implication, right? So if it's false, false implies anything. So you don't even have to look at what's over here. You can just short circuit it and say, okay, well, false implies something, so yeah, that's true. And so you don't have to worry if it's sorted or not. But if you set that thing to true, you have to also provide a proof. So I mean, this proof is always there, but it's just the proof is trivial, so you can get it by simp if you set that to false, or if it's sorted. So actually, this is pretty clever. I tweeted about this last night, or X'd about it last night, right? That if you say like 1, 2, 3, 4, 5, or 6, or whatever, okay, that's great. But if you put the 5 here, you're going to get a type error. And why? Because it's not sorted. But if you then say, well, okay, I won't claim that it's sorted, so the default is true. So if you say sorted equals false, type error goes away because now false implies this, and so it's good. And so anyway, that's the idea. The other thing I did, so that, in fact, I think I posted that to my little thread on the Zulip chat, right? Which I'll get to this in a minute, but yeah. So this is what this rake GTE used to look like, and now it's down to this because I don't have to, what I had to do was, I did the thing I wanted to do, which is this that mapping that I just showed a second ago, right? So A, that's been simplified because I'm not. I think that actually is the same, right? Yeah. Okay. So that's exactly the same, but these. This is the line I really wanted, but then I had to prove at every step that it was sorted, and I wanted to show that it was sorted by the less than, right? So I wanted the proof was to sort it by this operator. Only the problem is if you apply this operator when you do like your merge sort, right? So you notice I'm applying less than or equal to, whereas where here I'm asserting that they're less than, right? Because I want them strictly ascending, right? Or at least I wanted them strictly ascending. And I had to, in order to do that, you have to do like several steps. First, you have to deduplicate them because, basically sorted by this is saying that for every pair of numbers, this relation applies. Every number that is like early in the list and later in the list. It's not just the two next to each other. It's not just moving a window. It's every pair of these. Is less than or equal is less than, and so that means there can't be any duplicates because less than or equal is not the same as less than. So that's what I wanted. That's what I wanted to assert, and in order to do that, well, okay, you can actually run the list sorted merge sort by that thing, but it only works if you can prove that there are no duplicates, and so it's a little complicated, and so it's like this much code just to sort the list and come up with this proof that it's sorted by this operator. So you have to sort and dedupe. So so that was complicating the proofs, and this was right here was what I had to write just to show that it was so if I have the map, everything is easy. If all I have to do is map, everything is easy, and that's why it came out this short, because when you do a map, the size of the list never changes. But if you deduplicate, well, the size of the list changes, and so you have to prove once again that it's the same, that the list is non-empty, right? And so so every time I tried to maintain the fact that it was sorted, I have to also maintain that I have to do the deduplication, and then I had to show that it was it still had members in the list, or it still was non-empty, and so that was making every step complicated. I only have two main steps, but like everything was complicated, right? And so I basically had proven everything up until these last couple steps about the operations on the rake. So rake gets paired with a statement about it's a hypothesis that we have a bijection between the elements of the rake, or the terms of the rake, and some set. So or some predicate, right? So for all n, the predicate is true, and the predicate is just the property associated with the rake. Every rake has a property associated with it. Oh no, I'm sorry. Every rake map has property associated with it. So this predicate is a predicate on natural numbers. So it takes a natural number, returns a property, and for every number where that is true, we're saying that there's some number you can plug into the rake. The rake is like a function, like the nth term of the rake, right? is going to give you back that number. So that there's a one-to-one mapping, and it's bidirectional. So if there's a mapping, there is a, if the rake produces something, it meets that predicate. So that's, the goal was to make that happen on every move, and I had two basic steps that were in there, that I had to prove that for. So and they're totally properties of the rake and the rake sieve, right? So they are one, that there's a step that was called so rake greater than or equal, and then there was rake a rem. So that's removing the multiples of some prime, right? And that might even be a nat, right? But it's a natural number, but it's intended to be a prime, right? I dropped this. I just took this out because I'm looking at my time left, and I saw that, I'm worried that I'm going to run out of time, because I sit here rambling for 20 minutes, right? So I'm worried about that. And so I cut it out. I realized that I could just hard code the rake that I wanted. And so I took that out. So now I only have the rem step, but rem is based on another one called partition, and now I have sort. And I think I'm going to have to prove the following lemmas about all of these. Lemma is just like a minor proof, right? The one is that, well, it's these things, right? So that well, for partition and sort, the idea is that they're modifying the structure of the internals of the rake, but the actual terms in the that are being generated are the same. If you sort the constants, then the order that they appear, the term number 5 might be something different than it was, but whatever was term number 5 is still going to be in there, right? And vice versa. Whatever's term number 5 now was previously in there. So for that, I have to show that basically before and after is the same. That for every term that existed before, the term exists now. And then for partition, it's the same thing. But the operation that's happening is that I'm increasing the number of terms, of constants, and modifying the delta, right? So basically, you multiply the delta by 5, and then you apply the number 0 plus 5n. You compose the series that are there with the series 0 plus 1n, 0 plus 0 plus 5n, 1 plus 5n, 2 plus 5n, 3 plus 5n, 4 plus 5n, right? So that's the partitioning. You're partitioning by 5 there. And so you divide up the inputs. So the input is just divided into those 5 equivalence classes, and then, or n for whatever you're partitioning by, and then then you just have to change the sequence, and that will give you a different constant term. So you wind up with 5 new. For every one sequence you had, you wind up with 5 sequences. And then so you do those 2 steps. And they leave everything the same. They leave the terms being generated the same, but either put them in a different order or change how they're being generated behind the scenes. And then rem is like, the effect of this, when you did that, when you multiply by 5, is that provided the delta wasn't previously divisible by 5, now it is divisible by 5, and one of your every 5 numbers, you don't know which position it's in, but one of those 5 sequences has a constant term that is a multiple of 5, right? Like 0 plus 5n, right? 0 plus 5 times something is going to be a multiple of 5, and but you've added a number to it, so you have to rotate and find where it is in the list now. It's not necessarily going to be the first one, but one of them is going to be a multiple of 5. And every term or every number that that sequence generates will be a multiple of 5, and so we drop that. And I need to prove that that works. That's the goal here. Right, so those are the modifications I made. In doing this, right, in doing this sort thing, the previous steps, the GTE and REM, used to have at least a proof by sorry that they were, that they were sorted. Or actually, I guess, yeah, I believe they had a proof that they were sorted, right? Yeah, everything was proven except for that, and what I had left to prove was that these operations actually preserve the set, right? And that's trickier, and so I wanted to simplify things, and that's what led to that. So in order to make those proofs easier, I got rid of, or I changed the definition so that now it's only sorted if it says it's sorted, and that caused some minor changes that are going to bubble up into rake, sieve, and main. So these are now broken, and I was trying to get them working again, but earlier, and the two babies in here talking at me, and someone was at the door, and it was just too hard to do. So I'm probably going to do that sometime when I'm less focused and I don't have the quiet time, because I expect those to be pretty easy. They were. You're just basically propagating the fact that they're sorted up the list in a different way than you were before. But anyway, for each one of these things, I have these 3 proofs that I have to prove that they that if it's removing something. So this one removes stuff. This one removes things. It removes things less than the number, less than the argument. So the argument is n, and then it removes. It keeps everything greater than or equal to n, and drops everything less than n. And so I have to prove that it drops the right things, it keeps the right things, and it doesn't add anything new. So I call those proofs, I call them same, drop, and keep, I think. We have rem drop, rem keep, rem same. So we say rem drop, rem keep, rem same. This is my to-do list. But I think I have to do, I'm not dropping anything from partition and sort, but I think in order to do this work, I'm going to have to say partition keep and partition same, or at least prove that they're equal to each other, right? Maybe I can get by with a single proof that shows them, that has both the arrows left and right at the same time, but maybe not. I don't know. And then sort, same thing. So I have to show that sort doesn't drop anything. Sort. So this is what I have left. This is what I call the burden of proof, right? And that's a legal term, but I just think it makes sense when you're proving stuff. It is something you have to prove. So I have to implement that. I have to implement this. And you notice I don't have, so I took, like I said, I grayed this out because I'll go ahead and write them, but I'll just, well, it doesn't matter. Kind of for later, I want to do this just for completeness, which is GTE drop. I have to show that GTE keep and GTE same. I didn't need to retype those words, did I? So these I no longer need to do. So we're just gonna, and the reason I don't need to do them is because instead I just, in the rake sieve itself, or rather in here, I just, like like I'm gonna have to write a proof. I don't know how long these proofs are gonna be. So I just defined this. I defined greater than or equal to 2 as the slope is 1 and the constant term is 2. So it's 2 plus n. And 2 plus n is the arithmetic sequence that produces all of the numbers, all of the natural numbers greater than or equal to 2. So that's it. Yeah. So I also okay. So then I also did one other simplification that I hadn't really I hadn't actually introduced the complication yet, but I knew it was coming, right? And that was for this one. That because I'm doing not just the sorting set that deduplicates things, that I can always prove that if it had a term before, deduplicating it leaves you with at least one. So if there was at least one term before, then it had no duplicates, so you still have that original term. So that's an easy proof. But for this, it's actually like say you wanted to remove all the multiples of 1. Well, that's every number, right? So every number is a multiple of 1, and then you remove everyone. You remove everything. And you can do that. Now, the rule says you can only do that for the primes. Or my plan was to only do that for the primes, and I may make it so you can only do that for the primes. But what am I trying to say? Oh, so right. So the thought was that this is going to generate something that potentially wipes out every one of the sequences, and then what does it mean to take the next term, right? And so I didn't think I was going to be able to prove, or I thought it would be much more difficult to prove that it's not empty, right? So rather than doing that, okay, so if I was going to do that, I thought I'd say, well, okay, I will I will have this return, instead of returning a rake, it would return option rake. So an option being like it might be nothing or it might be something, and then so that's introducing a new wrapper, and then that would break this proof, and you know, I don't know. It just seemed like it would be much more complicated, and I think if these things hold, you're never going to run into that situation anyway. And so what I came up with was just, okay, you know, natural numbers in Lean work the same way too. Like if you take, let's do this, eval 10, and you subtract 10, you get 0. And if you subtract 100, what do you get? 0. Because there's no smaller natural number. And so it's just defined in that way. Subtraction is just defined in that way. And so rather than having subtraction return an option, you know, option nat, and then you have to, you know, figure it out every time, or, you know, doing what undefined integers sometimes do, you know, either they throw an exception or, you know, wrap around to some number, right? It just returns 0. It just sets it to 0. So likewise, I figured, well, I would just define a 0 rake. And so previously I had said, well, D is going to be non-zero, and then I was even going to, I think for one of my proofs, I briefly introduced the idea like D pos, right? That 0 is less than D, right? And of course that breaks. So I'd have to say by simp, and that would break this one, right? But instead what I'm doing is I'm just defining this, and so that I'm allowing this to be a valid definition, and in fact this gives you something, right? So what does 0 do? Well, you could say, if we go down to the bottom of the file, right, way down here, we can say eval terms is terms. Well, how about we say range 10 list range 10, and then we will map it to map those numbers into Zer dot term, right? And it's just zeros. It gives you a bunch of zeros. And you can also do this is property I think I want to preserve, which is you could say like def like site, it would be a rake, and it equals the D is equal to 0, and the KS is equal to 0, 5, 2, 7, or whatever. And then we can call that sorted false. And then if we get that range, not as error, but call that psych, you can see that it's repeating the numbers, right? So, do I need that? I don't know. But, maybe. Maybe it would come in handy. In fact, there's like, I could see a use for this elsewhere, but I mean, there are probably other ways to generate a list. Like, I bet there's a repeat. No, replicate. What's it called? Okay, well, I think there is a list repeat. Replicate. You can say replicate 5, 5, right? And that gives you 5 5s. I don't think you can do this. Oh, can you? Yeah, and then you would join it. Okay. So like these are equal, or I mean, if the constants were the same terms, these would be similar. Except this is a infinite one, right? So you can get the nth term at any time, and you can calculate it lazily. Is that useful? I don't know. I have no idea. But the idea was that this is going to be a general purpose library for this rake data structure that I might use elsewhere. So I given all that, I just decided, I'll let 0 be a valid thing, and then, you have to have something, and if it happens that you don't have anything, right, rather than having to prove this at each time, I can just check it, right? And I can say, well, like when I do the partitioning step, I can say, well, here I actually prove it. Well, let's see where the length is. Somewhere I do an if then. Oh, okay, here it is right here. In the rem step, well, I just check. If the length is 0, then I just return the 0th sequence. So if you do the remove of something and you wind up with no terms, then I just, rather than having an empty list with a because then what is it? If you don't have any constant terms, you have no sequences in the rake. So what does it mean to take the nth term? It didn't make any sense. So I just return zeros all the time. And so that's the idea here. Yeah. Anyway, I think we're caught up. That's enough rambling. So yeah, I guess I'm in the middle of moving this file out. So let's actually check this stuff in. I'm going to move the greater than or equal to operation into its own file for later. So I'm just going to leave a little note for posterity, like this was originally used in LeanSieve to provide the condition that the numbers were all greater, that the terms were all greater than or equal to 2. In the interest of time, I have dropped it so I don't need to prove. I have dropped it. I have left it unverified and moved it to this file. This file. May add it again later. So that's the first one. I guess I saved that now, so we got to check that in. And then for rake, I added that back. And then I'm going to go ahead and check in the rake. I'm going to go ahead and check these changes in. So those in, and I guess I will check in rake sieve as well. Maybe I'll check that in separately because it's broken. Checking those changes in is going to break it, but whatever. I don't really like that, but so be it. Oh, I didn't put a message in. All right, so work in progress. Remove. Clean up. Or say, remove rake dot GTE and use G G2 G greater than or equal to 2 instead. So then I just construct it from the start. I just construct that step from the start. Yeah, save it and and then this is broken. I'm just going to commit it in and say broken, broken partial update for. I really don't like doing this, but I don't think anyone else is using this code right now. They'd be crazy too, so it's just gonna be broken for a while. Okay. And again, it's broken because I've got to maintain that this thing, like, it's buried, like, so you've got a rake. The rake sieve contains a rake. A rake map which contains a rake, which has the sorted property, and it's just a mess. And I want to, like, put a couple layers on there to clean that up, but whatever. So this is broken at the moment, and I'm just going to leave it broken. All right, the important stuff is here. So we're down to this thing. We're moving the multiples of a prime, and I didn't even call it a prime. I just called it P, right? Just a nat. And I'll put this down here. I think before I do any of this, this is the plan. This is what I need to do. And before I do any of it, I was thinking I was going to make something that basically says, like a theorem that says, no, let me show you why first. Let me show you the problem that I'm trying to solve. Every one of these proofs that I've had to do so far, they use the word unfold, I think. Unfold, everything's unfold sequences, right? Unfold term, unfold this. So basically, at every step of the proof, like, oh, this is unused, but okay. So, all right, here. So, did I take everything out where I use this? Or maybe I just use. Like, surely the min one that you still has this. Well, okay, I did some refactoring too. I didn't mention this, but like right here. So I added this little simplification term myself, right? So maybe that's why this used to be in every single proof. So it's this big, nasty, complicated thing. So I have a rake, and I have a natural number n, and so I want to get the nth term out. So I'm going to call, so r is the rake, r term n is equal, and then I'm saying there exists some number k. Just given the fact that I have a rake and some natural number, there exists some number k such that the nth term of that rake is k times the delta, the plus, this, and there's some I that is less than the length of the. Basically, what this is saying is that for every term, what I'm going to do is I'm going to say, okay, I have 5 sequences here. I have n sequences. That's the number of sequences, r.ks.length. Ks is the constant, so the rake, the constants, and the length of the number of constants, right? I have that many constants, and I'm going to take one term from from sequence 1, one from sequence 2, and so on, all the way to the end. And so in order to do that, I have to divide this number by that length, and then take the remainder to pick out which one it is, right? So I is the index of the sequence that I want to look at is n mod r, right? So I divide by r. Sorry, not r, but I divide by this length, which is painful to write every time. Maybe I should give that a name that was smaller, but I divide that thing, and then I take the remainder, and that tells me which sequence to use, and then from there, that's how I calculate the term. And so the proof of that is that I do a d-sieve. So let's look at what this does. So to prove it, I say, well, okay, let I be just some number, and it is the number n that we provided as input modulo the length of the list, and so fin means it's a finite number. It is less than or equal, or sorry, less than this number, finite less than this number, and so fin is a type that is used for these kinds of operations, right? So this is a common thing for like bounds checking and stuff, or just setting a like a byte is defined, a uint 8 is defined as fin 256, right? Finite 256. And so when I do this, like if you watch over here on the right, well, this is like the thing I have to prove. And as soon as I step down, as I move my cursor up and down, it's adding this thing because I've introduced it into the context, right? So then I'm going to say, okay, I have to. The thing I need to prove is that there exists some k, some constant, right? And so the constant that meets all of these definitions is basically, they're all defined in terms of n divided by the length of the list, and so the constant that meets that is ks, the ith constant, right? So I just take that, right? And so use, what the word use does is it gets rid of that exists. So that backwards e is a logical symbol for exists, and as soon as I move down, you can see that right. It introduced this word case, but that's kind of basically the case is a general concept. Here, there's only one case, and that's that all of these things are true for k, right? All right, so then this whole thing has an and inside of it. So we have this term. It's this, and then there's this, and then there's this. But this is all one thing. So this is two. If I could, there's some way to make the parentheses show up. I don't know how to do that. But if I could fully parenthesize this, it would be, this is the left side of the and everything here is the right side of the and. All right, and then this has an and inside of it. But all right, so we apply and intro, and what we do is now we have two cases. Right, so before we have this red thing, and that red thing goes away, and we have these two cases now. So the first one is that the thing that was on the left side of the and the second thing is the right-hand side of the and. And so the left-hand side, or the right-hand side is, there exists some I. Well, I've already defined I, right? Like, I have to, I started out with this goal. This is a return type of the function, so that's what is causing these goals to come into existence. And I just define them the exact same way, right? So this meets that definition by design, and so use I is the proof of the second side. And on the right side, which is what I was building up to, is that I start out with this. So if you look on the left-hand side, my cursor is on the left-hand side of the line. That's like the before state, and then when you click on the right-hand side, you get the after state. So it changes, right? And so what I did here is, well, this is the definition that is provided up here, but I have to unfold that. So if I look at what term is, right, then as soon as I move my cursor after term, oh, I see. Well, it desynced it. So if you use unfold instead, rather than doing that, I'll do it on a separate line. So this is going to break that proof temporarily, but we say unfold term, right? And so now all this stuff gets expanded, right? That previously it said something else, right? It just said r.term n. Now when I move my cursor to the end, now it says all this stuff. This is the definition of r.term, right? So somewhere up here, I define what a term is, and it's all this. Well, term is defined, and it's doing that arithmetic to figure out which sequence to look at, and then picking that one out, and then it's calling the dot term on that. So first it's getting the k, and it takes the d out of here. So the k and the d terms give you an arithmetic sequence. Well, we actually construct one with the async function, and then so here's the k term for that, which is the thing I got out of the the constant I pulled out of the array, the list, and then here's the delta term that I got out of the rake, and that together gives me an async. So it says async arithmetic sequence k and d, two natural numbers, gives me an arithmetic sequence. And then this is like a piping operator, and it's saying these three symbols right here, pipe, arrow, greater than or whatever, a dot calls a method on there. So I'm calling this async term. So I've got an async arithmetic sequence. I'm calling term on it. The sequence is the first, it's like the self in Python. Like this is the object I'm talking about. So it's as if I said s.term right here. And then it takes a number, and that's the n divided by q, right? So of the sequences, if I have 5 sequences and I want term number 6, well, I'm going to wrap around, and I guess go back to term 0, term 1, right? Term 5 would be 0. Term 1 would be yeah, because you have a 0th term, so they would match. So term 6 would land on sequence number 1, sequence at index 1, and so I need to pass in basically the number 1, right? So sequence 0, term 0 is the first term of the rake, right? And then sequence 1, term 0 is the second term of the rake, and sequence 2, term 0 is the next one, and then so on until you get to until you wrap around, and then you're at sequence 0, term 1, and so on. And so that's what this is doing. Okay, so the whole point of that was that I have to unwrap all that, and so that gets inlined here, and then if I in order to make this proof happen, like to prove that these two things are equal, I have to keep unwrapping things. So I say, okay, well, unwrap async, right? So unwrap async, unfold async, and that makes this whole thing. And then I have to unfold, well, this dot term here. So that's async dot term, and then I have to so then I can use this I here, right? So that would be like rewrite I think. Hang on. Oh no, I see what I'm doing. Rather than shrinking this down and using I'm expanding this one. So this one right here, I'm going to put the word I here, and now I can't do that. I have to say unfold let, and now I becomes the I gets replaced, right? Yeah, so we can. There we go. And then, so then we have this big complicated mess, but you can just say simple, and it figures it out, and so that proves it. And then there's just a shorter way to write that, which is dsimp, right? So definitional simplification. So that's what that does. And until I extracted this little term simp command, I had to do that everywhere, and I had to do it twice for like every proof, because if you look at where this is used. Term simp, like here, to show that the min term is 0, I'm comparing two terms, right? I'm comparing term 0 and term n, and I want to show that term 0 is less than or equal to that, which is only true if the list of constants is sorted, right? So now I had to introduce this thing, but then I also simplified a little bit by so partially this actually got a little bit more complicated because of that. But at least I have it as a parameter, right? So I can pass in that this is a precondition, right? And so this term, it's a function argument, but it's a proof. It's a proof that the rake is sorted. Anyway, so there I used it twice, and I had to do it for the 0 and the n. And I imagine I will keep doing that again and again. I think I started already to use. Ooh, did my camera just die? Yeah, my camera just died. Okay, give me a second. And that's a nice little mugshot. 1 second, please. Please stand by. Like the battery died on there, but I have a spare battery. Don't know that if it's going to come back. If it doesn't come back, well, I'll just something. It's on. 1 second. Got a weird angle here. There we go, connecting, and I'm back. Okay, I should be back here. You should see something. There we go. And I'm going to zoom in because otherwise my green screen gets all screwy. And I'm back. A little behind the scenes action here. Okay. Okay, so what was I saying? That lost my train of thought. I was looking at this. Oh, I guess what I was looking at this to see if I was using that same. Yeah, so I had already started this proof of the drop. Basically, I got to this point and I was trying to prove this, and I started. I did this much work, and then I was like, oh, wait a minute, I have to do all this unfolding of this stuff. Like I had to like this is the line I care about, right? Like. I do this to do the greater than or equal to step, and then I had all this crap to do. And I was like, you know what, maybe I don't need to prove this at every single step. Rather than having it something I maintain 100% of the time, I can just turn it off. Because you can sorting is easy, right? So rather than proving that it's sorted at each step, I just when I need it to be sorted, I will sort it. And so I made that simplification. And then I saw that, I expect that, what does this say? The thing I was going to try and prove is that, so this is the discarded, this is this, right? This is GTE drop. So this is the discarded proof that greater than or equal to n actually works, right? That it takes a rake and the number that, I'm saying greater than or equal to p. And then if n is less than p, there is no term that exists, right? So in this one, I only needed one instance of that. But here, if I were to prove this, I have to show that there is some term in the previous state, right? This is, so here is RM rake, and then here is RM rake greater than or equal to. And it seems like I would have to do this same obtain thing. Like I have to simplify all that logic for each of them. And so that led me to simplify it this way. And plus, in the past, because, right, so even though it was, what am I trying to say? Let me collect my thoughts here. I'm trying to say that I had to do this, I had to do this step and do all these things, right? And this was written out in this proof. And basically, I realized that I was writing the same kind of thing that I had already written when I had done this, like the actual definition of GTE. Like I had to prove a bunch of stuff. And then here I was having to obtain all the stuff that I proved, all these little steps, right? Had I already done this step? I had not. Sorry, it wasn't this proof. It was whatever. Basically, I just kept having to do that same thing again, and over again. And I think even this is complicated, right? Because whenever I talk about term, I have to basically unfold the definition of term. That's the core of what I'm trying to say. And so rather than making every proof use term, right? Rather than doing that, I was thinking, well, okay, the proofs have to say that on the outside because I've already written this proof and I don't want to have to propagate that up. I mean, I could, but like that's already done. And there should be very minimal work to propagate the changes up, you know. Basically, I introduced this field that says whether or not it's sorted, and so I have to propagate the fact that it's sorted all the way up this little chain. So I have to do it over. I broke it here, and so I have to fix it in these two places, which is, you know, maybe multiple lines. But that should all be easy. But I don't want to rewrite all this stuff again, right? Because I'm running out of time. So what I want to do is, rather than have to write all this every time, I'm thinking that it might be to my benefit to make one more proof, and that is this, right? And that is that basically, how would you say it? So if we say rake dot term m, or term m equals m, would be, and ever since I started doing this, I love these little characters, and there's, right, I have to go back to VS Code to write them. So that this is equivalent to, maybe I should write it in lean, right? This is equivalent to, sorry, to the fact that something exists, like a k exists, such that a times so say rake, so r is a rake, and then r dot term, and we're gonna take a rake and we're gonna produce the fact, this is a theorem, right? Theorem, maybe term def, right? That there exists some, or maybe term if, right? If there exists some k in r.ks such that I'm trying to think how to say it without, like, what I want to say is that like there's some, you know, there's some variable, like we'll call it x, right? That you can multiply. So if you say k plus x times r dot d is equal to m, right? What I've been doing in the past up until now is I have been explicitly calculating based on this n. You know, I've been doing this. I should put this next to the. I'm doing that. I should put it next to this, right? The definition, the simp, wherever it is. Simp. Oh, simp is used everywhere. Oh, I know what I can do. I can go to this and look for simp. I don't see it. Yeah. Oh, it doesn't show lemmas. Well, that's useless. It shows theorems, but it doesn't show. Okay, so this is a theorem. Right. There we go. Now it shows up. I kind of wanted to show lemmas here. Okay. A lemma just means it's a theorem that's like not as important, but I guess this is pretty important, right? Anyway, so I was going to paste something, right? So I was pasting this. So rake term if there is, so for all n, and I guess at the moment x and m, no, not all x, but for all n and m, if term n is equal to m, then that is equivalent to some k in the list of constants and then right now I have to say this. I'm going to try to see if I can simplify this. Exists x, which is a nat, such that is m, right? This is the statement I want to make. And that's true, right? That's what the definition is. And so when we can say this and by, sorry. So I think if I do this, then it'll simplify things because I won't have to actually identify it. I'm taking a gamble on this. I don't know for sure. I don't know what that was. I don't know for sure that is necessary. Or that it will even be beneficial, that I'll even be able to make use of it. I suppose I could leave it as a sorry, and then only if I need it do I then go through and fill it out. But I also think it's going to be easy, so let's see if it's easy. Maybe I'll put a timer on this. I'll set a clock for 10 minutes, see if I can do this in 10 minutes. That's a scary proposition. We'll see. All right, speed. All right, what do we have? All right, we have a for all, so we have to intro n and m. Oops, n and m. Okay, we have this. So our term. So we have to say we have an if and only if. So we say intro. If we say apply if intro. Okay. That breaks it into two cases. We have to prove modus ponens and the reverse. We don't always have to do that. It is possible that these are equivalent. So what if we just say decent? What if we just say decent? What if we do this and just say decent, right? I don't think that's going to work. What if we say, but we have term simp rake, or our term simp of n. So we're bringing that into scope. So we have that this exists. And then maybe we can use that to simplify things. So let's see if that works. And then do this, apply, and before you do that, we'll just say simp all. I don't think it's going to work, but maybe it does something. No, we can try ESOP. No, it does some stuff. ESOP is like a automated. I don't remember. It's like automated search for proofs, but I forget what the E stands for. It's some search for obvious proofs. Automated something for search for obvious proofs, or something like that. Anyway, but it doesn't find it. So let's simplify it some more. So we'll go ahead and break it into terms using that. It's still good to have this, or at least it has been in the past. Maybe it's not because of this. We'll see. We'll see if I need this. Let's just have this handy, right? So we can give this a name like simp, hsimp or whatever. And that way it's in scope, and if it's in scope, it's a lot easier for it to see it. You don't have to say like you can actually say simp up here. I wonder if you, sorry, you say simp, and if you say simp, no. Yeah. Does nothing. Okay, interesting. All right, so I guess it's not a simplification. This is not a, yeah, simp only uses equals, right? So it would have to be like something exists implies something exists. Never mind, sorry. It replies, it uses definitional equality. All right, I'm off track. But this is how proofs work for me. Like you just kind of like throw things at it, and then you see if the simplification rules work. You can try, you know, stuff like that, and then you know, if nothing happens, well, let's move these up here. See, if you put the dsimp before, it simplifies it, and then you split it. And if you do it the other way around, then the dsimp only affects case MP, unless you say all goals. And now it affects both. But you can also get that same effect by just doing it before you do the split. Okay, so what does this say? Basically that maybe if we don't do it, then it'll be easy to read, right? So it says that, so that the term n implies that there's something exists. I think that is exactly this. So rather than having this, we can just say apply this. Apply r term simp n. R term simp, rake, apply term simp, rake, term simp, no. Oh, I see. We have to hang on. We now have, we've broken these into two pieces. We now have this, so we have to separate these two things so that we can get this as a simple term. So we're going to say intro HRT, R term n, right? So this is R term n. So now we have that, and then we can say apply this break term simp at HRTN. What is what? Oh, I see. So let's we have to specialize that. So we have to specialize. We have to pass it the R and the N, right? Oh no, hang on. Like I've already done that because I didn't just say rake. See, if I say have, this is what I thought I did. Hsimp. This is why I'm confused. Rake term simp, right? If I do that, you see, then it's this big complicated thing that takes the parameters. But here I actually applied the parameters. So I've already done this. So if I want to just use all them to simplify each other, I can just say simp all and see what it does. And it does do something, right? So if I can, not much, but a little bit. If these are the same, like if I can simplify this, it's possible that like this simplifies down to this. So what if I say exact and see if it can find something? It can't, right? And so I can also say ESOP here, and it can't fix it, right? So it can't do all this work. But I want to say exist k so that R term n equals k. Like this is saying the same thing. This is saying the same thing, but instead of this, what if I do this? So rather than saying that such a thing exists, because like that's all it gave me, right? Like this is just a hypothesis that there exists such a thing. But because I have the formula here, or just from the fact that you have this, you can obtain that thing. You can say obtain k and hk that is that thing. So I'm going to have the k that meets this criteria, which is basically this one, right? All right, so we have that. So now k is a natural number in our scope. Now when we apply the intro, we introduce. All right, so why did I do this? So once we did that, we had this r term equals m, and then that is this. So we can use that. Now these are definitionally equal, right? We can use hk. We could split this up into different pieces. In fact, I can obtain hk, hk1, sorry, hk2. Right, we can break these into pieces, and so hk3, right? hk3. Now I got 3 statements about that. I'm gonna call this hk0, right? We can just split those ands basically if we need to. And now maybe we can do simple. Did some work, but not enough. Okay, we could do ESOP. I think ESOP generally doesn't work so well after the until you do the apply and the intros and all that stuff. You have to do some manual work, and then it works. All right, so that didn't help us at all. All right, so once we've done this, we have 2 goals. Oh, there's my time. That was my 10 minutes. All right, so on, let's do this. I'm gonna just structure it out. Sorry. And sorry. And then if we do that, you see this sorry is now redundant. So this is the proof, and we just have to fill in these sorries. So these dots say we're gonna do the two cases. You can either give them specific names or whatever. Like, the names are kind of long and nasty. All right. Again, I'm going to defer doing that for a while. So now we say use k. So I had a k, it has all these terms, and now we can do that. So before I did that, we had to prove that some value named k exists. So this is like it works like it introduces a new scope. So this k is not the same as this k, but I can make it be the same as that k by saying use k. I'm going to say this k right here is going to be this k right here. So basically apply that. And then once I do that, now I think simp all works. Yeah, and see, we got a squiggly line under sorry, so that's enough. And that completes the proof. So all of that got proven that way. And now we have to go the other way. And so the way we do this is going to be almost exactly the same, but we have to prove it from the other direction. Like we're proving this right here, and that's what caused us to do the if and only if intro, and we have the 2 cases, right? So we have to prove both directions of that arrow, and so it's going to be about the same concept, but we're going to go in the other direction. So first we have to introduce this hypothesis. So we have to we have an implication here. This implies this. So this thing, and then the arrow is an implication. That works just like a function call. And so we say, okay, if this were true, the thing it's asking us to prove is this implication, meaning if this is true, then this is true. So we can say, okay, give me this fact. Assume this fact is true. And the way we do that is we say intro, and we give it a name. So it's like backwards from when instead of defining something with a name, like we have the value and now we're giving it a name. Like usually when you have a function, you say, like here we say R is a rake. Well, here we have the value, and now we're giving it a name on the fly. So we're going to call it HK, right? Or we'll call it K exists, right? Or we'll call it HX, hex for exists. All right, so now we have hex, which is that this exists, and then here's what that we have to prove now, which is this, right? And so the when this was the main goal, we said use. Now we can say specialize. So we say specialize specialize hex, and we give it K. Oh, that did not work. At hex. Oh, I may have to go back to. Let's see what specialize does. Oh, it breaks my language client for one thing. The tactic specialize works on a local hypothesis H, so it should be specialized. That's right. Specialize hex. The premises of this hypothesis, either universal quantifications or non-dependent implications, are instantiated by. Oh, it's for alls. So specialize is for all. Right. The one for exists is a weird thing. It's like, let's see if I remember it. Cases hex with K. No, because you can see that made a new K. All right, I have to look this up. And I had a bookmark for this, but I don't think I have it anymore. Where did I see this? Where did I learn how to do this? I learned how to do it. Maybe I have it somewhere over here. In the browser you can't see off to the side. It's in a course that was called the Lean for Tactic cheat sheet or something like that. That's it. Oh no, that's not it. Wow, there's a lot of cheat sheets. I'm pretty sure this was made by Kevin Buzzard. This is it. Formalizing mathematics. It's for the Xena project. But I didn't want a PDF. All right, we'll try it. There's an HTML version of this somewhere. Probably right here, right? Man, that's annoying. I like. Well, okay. Maybe it was this. Project Xena is it's this book. Project Xena is like his. He's a professor at this college, and he's Kevin Buzzard is like a mathematician that has done a tremendous amount of work to popularize formal proofs and especially Lean and getting like mathematicians on board, and he's got his students doing proofs and whatnot. Anyway, this because this is so weird. Cases H, right? So instead of use H, we say cases H with XHX. I should have set another timer right now that I lost my time. Cases, I don't, that was it. I was just at cases K and HK. No? with an inductive type. Cases n. You use an expression instead of a variable. I don't think this is the right tool for the job. Let's just do this again. Let's try. So what do we have? We have we don't have to do anything with this. We just have to prove that this is true. So what do we know about M? We know that this is true, right? Oh, no, we know this is true. Ah, this is wrong. This statement is wrong. It's not for all n and m. It's for all n. There exists an m. Okay, so we intro n, and now we have to break this a little bit. So no, hang on a second. No, I'm doing it wrong. For all m, so if a term comes out, then if there exists an n that you put in, there we go. It's still complicated. It's not going to be quite as, it's still going to be a more complicated proof. So I'm going to have to redo this. Right? We introduce n. Okay, so what's changed? We've introduced n. Oh, sorry, introduce m. And then there exists an n. Okay, so now what do we do with exists? Well, we would say use, but we don't have anything to use yet. And we can't do this until the step. Right. Okay, so all we can do right now is split that. Right? So we do. What? And you can't do intro, right? You have to say exists. I can't show that it exists. What do I do? But I can't say what I want to use. I think I have to prove that it exists. No. This n. No. Ah, I need parentheses. That if this exists, Yes, right. Okay, that now we're good. All right, so now we introduce this. And now we can do the if intro. And then, right, because otherwise it was saying that n was for both sides of the if and only if, but I only wanted it on this. N is only mentioned on this side, right? So I'm trying to get rid of the need for n, right? That's the whole point of this thing, because I'm feeling like I have to. Right now, I'm using term simp. I'm expecting to use that in every single proof, and I'm going to have to like say, well, okay, it's this number modulo this number with a remainder of this and divided by this, and like that's all nonsense. I don't need to know that which n it is. I just need to know that if there is some n, then that also means that there's some k in the list of numbers that I can look at directly, right? I don't have to worry about which one it is. That's what I'm trying to get at. And so I'm going to turn that n into this x, right, which is just basically n divided by the list of the length of ks, but I don't need to know what that number actually is, right? And I don't need to know what the modulo is. I don't need to know which one of the k's it is. I just need to know if there is one, right? That these two things exist, that these two things imply each other, and so then like that's the goal. That's why I'm doing this. Okay, so. So I guess really on both sides I can intro, we call it like hx0, right? Like the first thing, oh, why not? Oh, because you can't do it here on both sides. Now we can do all goals and we can just introduce intro x0. You can't do that when it's with a two-sided arrow, but once you've got two one-sided arrows, now you can introduce something on both of them. So all goals does the rest of the line on both sides. So you can see it. It got rid of both of these and now introduced hx0 for both sides. They're different. You know, on one side it introduced this, and on one side it introduced this. It just they're both exist. So whatever. Okay. All right. So we have that in the world. What do I want to do though? I want to. I think I can do it like this though. Like I can say, well, right. So in order to get rid of that exist part, so I want to actually do it. I don't want to do all goals. I want to do the same thing, but on two different ways, right? So on one side, I want to have it exist n. So I'm going to say intro n and hn, right? And then on the other side, I have k. So I want to say intro k and hk. Hk. The little dot and the indentation also introduces a new scope. By the way, I see people are watching, so welcome, hello, thanks for watching. And if you have any questions or comments, feel free to type in the chat. Otherwise, I will just continue talking to the air, which is my normal way of doing things. Okay. All right, so this is kind of garbage now, so I'm going to comment this out. This is what I had before. All right, so again, we have sorry. This kind of keeps it syntactically correct, even though you get a warning for using it, but that's okay. That just tells you what you need to do. Okay, so I think we're good now. So here, it's the same logic that I did just a minute ago, so I'm going to bring this back. So we want to prove that this exists, so let's obtain it from just doing this thing that's already defined that we know we can do for any rake. Then we say use k and simp all, and I think that works. Did it work? No. Rather than do that, we'll say use k, and then it looks like we have, what's different now? Because now we have an exist x that, well, we can do simp all, see what progress we can make. Yeah, that didn't work. Why? I expect this to work. All right, we can apply and intro to break up these two sides. I guess I've changed this enough. So now we're looking at, like, it says 2 goals, but really there's, wait, if you go up here, there's what? Okay, I'm not sure what. Sometimes this display is a little weird. Oh yeah, so we've got unsolved goals. We got the right-hand side. I was missing this. All right. So we use k, apply and intro. So show that k is an element of RS. That should follow right from this. So now that should be simp all. Nope. Can ESOP do it? No. Use HK3 exact. Huh. Oh, I know what I didn't do. I didn't do this step right here. No. Wow, okay. Why is it suddenly harder? I don't get that. A is an element of RS. I mean, this proves that. All right, so that would be it. If I had to name that term, if I had to name a lemma that proved that for me, I would look for first the documentation for okay. Lean for mathlib documentation. There we go. So I would call that list mem of get. Or mem if get if get. Yeah, mem if get. There we go. Mem if and only if get. So that if I can say this, and that, so I can apply this. I can just have this in scope. And so I could say have this. I really should set a timer on this, or at least written down when I started, but I've been at this for an hour and a half. Okay, total for the video, and I think probably half an hour. So I've probably been at this for, I don't know, less than an hour. All right, so we have this thing in memory now, and I think, where did it go? Why isn't it there? You have to so have H. What is? We'll give it a name. So now it should be in memory. It should be in. I just want to. Well, I can use this as a rewrite rule. Okay, so I can rewrite it with this. Rewrite list if. And then I think that's exact HK3. Exact. Ooh, that's ugly. What if I do that? If I do this rewrite at HK3. At HK3. No, that didn't work. Oh, it's not HK3, it's HK3. A little number there. So okay, I had it right. Go at HK3, but it still didn't do anything. Why didn't that do anything? Because it's not this exact term? Right, it's not that it's really this. It's HK1 and HK3, right? I think just have, okay, so let's say simple with this in mind, with that little thing in mind. Did it help? No. Simple only. No. Oh, yeah, kind of. Is this N? And then we say use K? Use K. Oh, that didn't work though. Exact is not finding it. Okay, so I have to have that in memory. What did I say? I said I rewrote it with this. And then exact gave me exact question mark does a search and it finds this. And I can just put that in and then that I've solved that, but that's just ugly. Like once it's that messy, it's like you might as well just say that, you know, you solve it by magic, right? But that doesn't work. So say use K and then ESOP. No. Simp all. Somehow I've got a sorry in there. All right, so we write it with we rewrite this. Like in my mind, these two things say the same thing. After I rewrite it, maybe I could have sworn I just had this a second ago. Is it decent? Oh, it was simple. Simple did that for me. No. Well, okay. Now this is a different thing. Like I can prove that this right here meets this criteria. I could say use n over. I mean, that's not what I was going to do a second ago, but r.ks.length. And then now simple should. Oh, come on. Yeah, okay. So ESOP got me part of the way there, and then it improved it. So it got me this far, and then you can see that it's. I know that this is like hard to talk about because like it's happening too fast. I know that, but you just type things in and like things change over here, and sometimes before I get the sentence out, I realize it's wrong and it's whatever. But like yeah, so ESOP got me this far, and then it's like this is not the like what does this proof mean? I don't know. It means that like this was obvious to me, right? Like it like the whole reason I made this thing is because like it's an obvious thing to me, but I knew that like Lean would have to make me jump through hoops to do it. So whatever. All right. So I don't know what that means, but it's true. Right? That's all that matters. Like it's obvious to me, and then there's some mess that proves it. Okay. Ideally, when if you were to publish this, you would. Isabel has a format called or a journal called the Journal of Formal Proofs, the Archive of Formal Proofs, or something like that. And they have a thing called a proof outline that just shows you these things, right? And you don't have to see the garbage inside if you don't want to. And I think Lean has some tools like that too, but they're more for like if you're starting from LaTeX, there's this thing called the blueprint. You're starting from informal math or whatever. Okay, so where are we at? Anyway, like this is just nonsense. I have no idea what any of this means. I just know that's true, and this is how you prove. This is one way to prove it in Lean. Sometimes what I like to do is go through and after the fact and like try and clean it up a little bit. I don't. Oh. There we go. Yeah, the ESOP had a yellow squiggly underscore, and I didn't like it. I think it put the word sorry in there somewhere. Like in behind the scenes, it was using a sorry, so it would have kept this yellow, I think. Anyway, you don't like ESOP is doing something like this is what ESOP produced. If you ask it question mark, it tells you over here what it did, and you click on it, and it puts it over here. So it just generated even more garbage for me here. So this is a lot of nonsense. I don't even know what it means, but here you go. Actually, I've never seen this subs tactic. Isn't that like rewrite or? Hmm. Interesting. anyway, sometimes if you see it, like, it gets you, like, if it, like, it looks like this is just the same kind of stuff on both sides of it. So I knew that there was probably already a lemma for that. So then I just typed exact question mark and then it proved it. And then again, if you click over here, then it tells you what it did to do it, which is this line right here. All right, that's that. Okay, I'm gonna set a timer again for this one, just see if I can do it now. 10 minutes. Probably not. That's the problem. It always takes longer than you think, and so that's why I said, oh, you know what? I'm just going to cut out all the proofs for greater than or equal to, because who knows, right? It looks like they're easy, but if you can avoid the proof, maybe you don't spend an hour on it. You know, maybe you save yourself an hour. There's no telling how long it's going to take. It's a search. It's a puzzle every time. I guess I am spending less time searching for, you know, like tactic names and things like that. I'm getting better at searching, but, you know, and then like I changed something up. I changed these parentheses and like the entire proof changed, like something that was like 2 lines to this complicated. So I'm now at the point where I'm wondering if this is even worth it, but I suspect that this kind of pain would have been that I'm going to have to, that I'm avoiding this, some amount of this kind of pain for every single one of these proofs. That's what I'm hoping. That's the bet I'm making here. Bet I am making. Not bet. Okay. So again, we have this. I want to use something here. Did I use this here? Yes. But I think hang on. I think this is again where I want to do the same kind of thing. Instead of introducing this, I think I want to have this in scope. This obtain up here. Oh, but I don't have it until I have n. Okay, so I can't do that. All right, so we're going to say intro k, or we're just going to say intro h exists for now. Let's just enter that. So we're going to leave that there for now. And what do I have to prove? I have to prove that it's weird that I have existing on both sides, right? Because I'm not relating the n to anything on this side, and I'm not relating the x to anything on this side. I'm just saying that 2 things exist simultaneously. If one exists, the other exists, and I can. The idea is that I'm hoping that if I have a goal like this, I don't care what n is. I just rewrite it to look like this, and then I don't have to do all this nonsense. And that's why this is complicated. That's kind of the nature of what's making it tricky to make these proofs. Like informally, it's kind of obvious, right? like informally, like this is true because this is what our term means, right? If you unfold all the definitions. Whatever. So here I do want that. So we're going to say use. Yeah, I think instead of intro in that, we have to obtain it, right? So obtain. So intro x and obtain k, and I think you just say k, intro k and hk. Intro K and HK, right? And we can split that up and we can say HK, oh, like this. HK0. But these are different ones. There's only two of them. Well, I mean, we can define X in terms of this exact thing, right? Like we can simplify that, right? We can say specialize. Like I thought I would have to like do some weird, like I can just use math to say what this is. Like this number is just K. It's M minus K divided. Well, it's not though, is it? If these were rational numbers, this would be. All right, so specialize H. All right, so we'll call these HK and HX, right? So specialize HX, and we have to give it something to specialize it with, right? And we're going to use. No, it's not. It's not specialized. I do that again. It was that thing I just looked up. Like use cases H with X and HX. Okay, so specialize the cases HX. I don't understand why this is the word. I think this is like cases just happens to work out for this. All right, so we're replacing HX with a new hypothesis, X and HX prime, right? No? With. No? Because we already have an X? Why is it? Why didn't that work? I'm expecting to see cases haven't exist, right? And it's in the hypothesis named H. So cases HX, right? X and HX. Unknown tactic. What's wrong? Why is this broken? Cost 8.0. Why is that wrong? Unknown tactic. It's right here. I just used it. I did this a second ago. I feel like I did this a little while ago, just a few minutes ago, and I'm down to 20 seconds. Okay. So this is not this is me getting confused, right? This is me thinking I knew what I was doing, and then suddenly, okay, I don't understand why that does not work. First of all, I know why. It's because I did this. Okay, that's part of it. I had brackets. No. Nope. I was correct. The brackets were correct. They did exactly what I wanted them to. And now I have to prove is it because that letter X is there? Q and H. No. If I just say cases HX0, what does that do? Like, I do not understand at all why cases is the word to use. But we could call W and HW with WHW. Why does that work? What if I move it over here? No? Why does that work? So that worked. That cleared the error. But I'm not clear why cases sometimes works and sometimes you need that apostrophe. I don't know why that is. Sometime I'll figure it out. Okay. Like that's exactly what I wanted to do. I just want to call it X and HX, right? That's what I wanted. I have no idea what this apostrophe does. I guess I could look it up. We could see, how do you say health, tactic, cases, apostrophe. It doesn't say. Hard to read. I don't know. I've seen this in the docs, and I could not explain to you. I don't remember what this does. I know I've seen it. I don't remember what the explanation is. It's just a variation of cases that sometimes work. So I guess if cases doesn't work by itself, try an apostrophe. Okay. And then we'll just call it magic. All right. It's not magic, right? Like what this is doing behind the scenes is doing a lot of meta programming that is, constructing something that is just a bunch of function calls that cancel each other out, and but it's hiding that the work of constructing those function calls from you. All right. Yeah. I feel like I've been having fewer of those like what the heck moments with Lean, but I still get them. Okay, so now that we have this in mind, now we can find this, right? Because we don't know anything about our term. And we're trying to prove that a term exists. So all we have to prove though is that okay, so, but I think we can. Well, I think what we can do is we can simplify apply these definitions. So unfold term and all that stuff. Hang on. So I had this thought a little while ago. Rather than doing this, which is what I did up here, let's do this obtain step, right? Won't work. Could I prove this by contradiction? I think that might actually be easier. If I say this does not exist, I think I can prove this by contradiction, right? So we say by contra. So now that should turn into a it should turn into a, we'll call it by contra h. And if I say absurd h, that exists again, but that's not what I want. No. How do you do this? How do I? All right, so we say by contra h, there does not exist n such that r term n equals m. If I had an n, I could. If I knew what I don't even like hypothetically know what n is. N is like it's like a thing I don't have. And I have to work backwards from the definition. And I know it depends on the index. Okay. Didn't I say something like mem and get? I had this. I need the opposite of this. I need this. This is the index of k in that list. Okay, so I can use that. That's what I want. It's the exact same thing, but backwards. All right, so k is an element of RKS. And I can rewrite that with this. So rewrite at HK. All right, so, okay. So now there exists an N. Can I call it at HK? Okay. So I'm going to say obtain. The N is the index. So I'm going to obtain I and HI, right? That the hypothesis about I is equal to HK. I think I can say that I'm just seeing if I can shorten this. Does that work? Right, but what that gave me was it erased HK, and instead it gave me a K in scope and an I and an HI that says, you know, so K is this. Okay. Now I can work backwards from this and M to determine what the N was. I have to work backwards to tell me what term that was, because I know. Well, if I do these things, it's going to make a big mess. But that will have expanded the thing, and I could say that right? So we have X. I think I want to. I like right now. I have an arbitrary X, but I want X to be. I want to use. I want to unify these two things. X is right. Like this is I. Look, I mean these are the same. Oh, sorry. K is equal to RKS get I, right? So this is RKS get, and this is I right here. So M is equal to this thing, and then I can simplify. So X X is this over here. So here's RD times this. So X is N over RKS length. Yeah, I need to leave this. I need to leave this as an existence, right? It has to remain like just in existence land. But how? How do I do that? Because I only got this far by I know how to. I think if you want to force a unification, what if you say? I think you can say this. I think you can force the unification by saying show. Right. So let me. Unfortunately, as soon as you type show, it erases what's over here. So I'm going to copy this, and I'm going to say paste this in here. And I think as long as, so RKS get, no, okay, let's just say RKS get I. Let's see if, I think I can do this. I'm not, I think maybe I can do this. So we're going to say, we're trying to make this assertion, right? We're trying to make these unify. Force unification. Attempt to force unification. I want to do that, and I want to say this is X. X. What if I say and? What if I say this and x is equal to this, and I don't know if this will work or not. Can I say oh, not this is not, and x equals that, and but this doesn't exist n such that this is true. No. But that would imply that n is equal to I would say use n is equal use for n. I want to use r dot ks length times x plus I. No. Hang on. And simple. No. And then rewrite with the reverse of I want this hi. I want to simplify this with hi. Actually, that's just simp. So simp hi. No, that didn't work. Rewrite with hi. Did not work. Oh, hang on. Maybe this is not right. It's not this. This can't be right. I did the wrong calculation. Let's just give this a name. Let's introduce this by saying what do we want to call this? We're going to call this thing not an x. We'll just call it y. Y is equal to this. So let's write a slightly different I plus x times RKS. And this is going to be hard to prove, except that I've done several of these little modular arithmetic mod div mod stuff a couple of times. Okay, so we're going to use y. So we have a definition of y here now. And we're going to simplify this. Okay. So now we have to show no, that's not right. It doesn't matter. So I'm asserting that I is equal to this. So we're saying have I is equal to y mod r dot ks length, right? I mean that's clear because this is a multiple of that plus I, so this is the remainder. And that's true because I is a fin set, so it's less than the RKS length. And that would only be true if that's the case. And so how do we prove that? So we say we have an HI. we have this, so now let's have hi1 is this, and this is going to, let's call this hi0. Just a hypothesis about I0. So this is from here, from simplifying y. So I think omega can solve this. Nope. ASOP, because you can't. Right, I said it was going to be hard. It is going to be hard, and it's going to be hard because of this. I have a file called nat over here, or sorry, natdiv. I have not checked in, but it's all these things that took me like hours to prove that are very simple facts. And like it took me 4 hours of struggling to try and prove some simple facts here. And I posted on the Zulip chat, like, you know, before I went to bed one night, I said, like, you know, hey, is this hopeless? You know, is there any way to prove this? Because I know that the problem, I don't have where the problem is, but in the scratch here, I have something like, it says the root of the problem here is that if A is less than B, A divided by B is 0, right? So you lose some information, and so you can't just do like normal arithmetic, right? But there's some thing. So what Yale showed me, Yale, I don't know what their name is. I don't know how you pronounce their name. Yaell, I think is a very advanced user of Lean. They've written some papers and stuff. All right, so and they helped with some questions. So anyway, they told me they solved it in like 10 minutes, like 2 minutes. Like I they didn't understand why it was hard for me, and then I said, well, you know, it's still hard. Like, you know, they were quibbling with my syntax, and I was like, you know, okay, whatever. Because I'd use like the not equal as a logical operator, and they're like, why do you use that? And I said, well, how do you express XOR or whatever? Anyway, so they were thinking that's why it was hard, and they were saying, well, you could just use this, and then the answer is that I just thought this was a logical operator to me, because it is in J and APL and all that stuff. Anyway, the point is that they didn't, that once I said I still don't understand how to solve it, even if I simplified it by only doing, you know, one side of this. Like here, I'm doing this, you know, I have to solve 2 cases. So you change it to, you know, this is the opposite of this, right? This is not, right? And so you can change it to the left, right, and then a not on one side, right? And so that's the, you know, so you say X and Y. Okay. Anyway, the point is, you know, because not equal and if and only if are like the opposite of each other is what I'm getting at. Anyway, they thought that was my problem, and then I said I still don't understand how to do it, and then within like 2 minutes they had an answer, right? And so that tells me that the thing that I struggled for 4 hours to find, they were able to find like instantly. And I said, how did you solve that so quickly? And then they said, well, they made a joke about having a tactic that had their brain encoded in Lean. But they're just really good at this, and so they're familiar with this. So the tactic they used was this one right here that I saved but did not record, which is like, this is their proof. It was div add mod, and so this is like the magic thing. So somehow I'm you can use that or one of the tactics or terms, proofs like it. So okay. So what am I? So let's look at this function, div add mod. Div add mod. Div add mod. We're saying that we have the first argument is m, and that is the one that is the thing we are dividing. And we have this in this form, right? Oh no, we don't. How do I construct this proof? I have this fact. Maybe I'm actually looking for something different. What do I want this to change to? I want this to change to what? Well, I want to prove this, right? Y times RKS length. This is what I want to do, right? Because then I can use it as a substitution rule. Well, I have this too. So okay, so maybe if I had this, if I can write it like this, m mod k. All right, so let's have this. I have I is equal to I mod r dot ks length equals, and that's I dot prop. So have, okay, is exact what? Come on. It's this. This tells me that. Oh, I have to say by exact. That's what the definition of fin is. By its type tells me that. How about I dot, we say we have to unescape it. So up arrow of I is equal to up arrow of I dot x. By exact, you find that? No. Have I dot val is equal to I dot val. By exact I dot prop. By equals I dot prop. What? What is I dot prop? Have I dot prop. Oh, it's less than. Of course, right? It's less than, right? Duh, sorry. No, wait, I is less than R, and then now we can say this. Have, because that is true, now we can, right, so the property is that it's less than, and then we can have that. We can say I dot val mod, and that is by exact something. I don't know what it is, but yeah, that's a rule of logic. Okay. And we can just say I dot prop. Okay. And I think we can even just say like this. Okay. All right, so now we have, did I move? Yeah, move something. No, I didn't. This is what I was looking at? This, okay, so I have this m over k plus k times m over k. And I think I can say that that k times x over k is the same as k times something else over k. And I'm going to, I think, let's see. Okay, so we have this. So let's call this hi, again, hi1. And this is now hi2 if I need that. No, that's what I wanted to prove. Okay, so we have that. And we don't need this because I inlined it over here. All right, let y equals this, use y. And then now we have this property. Basically, the idea is that I need to have, so I have I plus x times r. So wait, y is I is this, and then I is this. So then together, these things say I have that y is equal to I divided by r dot ks dot length plus x times r dot ks dot length. Right? In fact, rather than trying to prove this, I can just define y this way. Right? I can just define this y this way. Then I can take, then I can take this fact, and I can say simp this. No, I can't. In fact, I see this sim in here. Maybe if I just reverse this, it would be a shorter thing. Equals I by exact this, right? I don't even have to do that, right? And then, so now we have a rewrite rule. So we can say simp this. Huh? Rewrite this? No. Okay, hang on a second. I haven't proven enough yet. I need to have, so we say have y div mod, is that, I call this function mod add div, right? Mod add div. So y is the m, right? And then divided by k, so we want to say r.ks.length. If I say simple, does that do anything? No, I can't do anything. Let me make this wider so I can, hide this, make this wider. Move this up a bit. I think I'm going to need this in a second. Let me just hide it for a minute. And y is defined as this. So can I have like I guess I want to prove what I want to prove is that I is equal to y div r. I think there's a different rule here. It's more like an if then, right? Like a mod add if. Like nat maybe this? No, it's like add div. It would be like mod add div prime. What is that? Mod add div prime. Unique. Okay. This is a little hard for me to parse. Okay, so we're saying if A over B is D, okay, and A, that's the same as saying this. Can I rewrite? Can I substitute something in here so that this? I feel like I can. That this is somehow going to wrap up being. So here we have the div and the mod. We have it as two separate facts, and then together that. So it's fine. So we have the div and the mod. So this is like D here is like let's rewrite this. So within here. I'm just gonna introduce something to give me a B, C, D, like a scope, right? Right. So say have for all A, B, C, D, then comma this equals what's wrong with that? Maybe I gotta put this in parentheses. I think we have to say lambda A B C D nat div A B C D. Oh, come on. Oh, and 0 is less than B. It does not matter. Whatever. It does not matter at all. I just want to write these things so that I can that I can because it's so hard to read. I'm gonna hit F2 in here, and I'm gonna say this is r.ks.length, right? And let's rewrite it like that so we can. Well, maybe we'll see it like this. Okay. All right, so then A is what? So so A is Y, right? No. So what do we have? So C. Like I want to put. Like I want to derive something from this. I want to derive that, like. I see. I want to take this statement and use it to derive this statement. Hang on. I know what I can almost put it together in my head. It's like I know what it is. I have two statements like this, two sets of statements like this, and I want to apply this transformation from here to here on both of them. So that I can derive a rewrite rule from that I can like, if I can have this is equal to, like, right. Let me just write it like this. I have this right here twice. It's too hard for me to say this verbally, right? What do I have here? I have well, I is, so we said B is r.ks.length. Okay, r.ks.length. B r.ks dot. Same thing. I know what I'm doing. I just don't know how to. It's just too complicated to put into words. I can see it in my head, right? Right, we got this. So that's always going to be the same. And then we have, this is I, and in statement 2, it's y mod r.ks.length, which is a big complicated thing. Usually I call this like, I say set, I call this the remainder, so I call it like yr is equal to y mod r.ks.length. And that will actually rewrite it in here, right? It should, it was meant to. It's supposed to rewrite it right here. I think it's because it's inside this thing that has a proof with it, right? So that's okay. All right, so we'll call this YR. What I'm going to do is I'm going to make these two definitions. I'm going to say set YR, and then I'm going to say set. The other one is YQ, so the Y quotient and the remainder. And this is Y divided by r.ks.length. And then I'm going to say, so you see it simplified it here. And I'm going to rewrite it like this and show YR. Oh, sorry. Okay. There we go. So I forced it to rewrite, forced it to unify. Okay. So then right here, I say, now I can call this YR. That's RKS. And here, this is, these ellipses right here, or this ellipsis is what it is eliding is the following proof that have HYR equals Y is less than, YR is less than r.ks.length, which is a fact about natural numbers that we unfold let. Oh, sorry. It's complaining about that. So there was some exact here. No. Unfold let exact. Surely this is a. It can't find it. Whenever you have scratch stuff down here like that, that's what can cause problems. Sorry. Okay. Get rid of this. Right now, did it find it? No, it's still looking for it. You can see it's all green here. It did not find it. No, these are just added lines. What happened here? No goals. Sorry, exact. Do I need this hypothesis? What is this? This should be a theorem. Have mod nat mod less than or equal. We have to prove that it's not 0, or rather that r.ks length. So we need. So in order to divide by y, we have to show that y is greater than 0. So we have to say have r.ks length is greater than 0, and that is why that is a property of the rake. So r.h size is that exact property. So then we can take this of yr and r.ks length, or actually we just say r.h size, and that's it. All right, so that's all we need. And now I think that's the exact proof, right? No? What's wrong? You can't see that because my head's in the way. I can hide this, right? And move up. So it's weird. It exactly fit the curve of my little circle. Nat mod lt yr h has type. So this is the type we have. Come on. You know you have this. Wait. Isn't this what I want to prove? Oh, yr. Oh, so I need some other thing. Okay, so once I have that, I also have to say have. I just did this a second ago too, didn't I? I probably deleted it. Wait, this is what. Wait, do I need the fact that I'm? Wait, hang on. This is what I need. I had OIR. I need y divided by that. It's less than that, and then dsimp yr, and then that's the proof. Right now, it's exactly the same. It's exact. Right? So the mistake I made was I typed yr here, which is redundant. Like I need to. Right. So then it's just exactly this. It would be exactly that. Say we have. Actually, we say. Right, so we dsimp y first. Hang on, we dsimp y first, and then exact this. And that's the whole proof of that line. Okay. Okay, so now that we have this is the kind of thing you're always like, you have to prove these like ridiculously simple things, and I really suspect I will have to go through this hell for every single one of these proofs if I don't do this proof that I'm doing right now. That's my guess. And then once I have this nonsense, I don't have to deal with this modulo, length of the list arithmetic at every single step. I just have to say, is there some k that exists? Is there some constant? That might wind up being just as hard, but that's the goal here. It's 2:30 in the morning here, so I'm gonna finish this proof and then I'm gonna call it a night. I was hoping to make a little more progress, but whatever. I am gaining experience with each one of these little struggles, each little battle with Lean, and that's why I'm worried about time. Okay. Didn't I start out thinking this whole proof was going to take 10 minutes? It's ridiculous. It just does not work out. But I'm having fun. I do enjoy this. It's like playing a video game. That's what they always say, and I agree with it. It's not. I'm not the one who originated that thought, but it's definitely the feeling. It's like a little bit of a game. Okay, so now that I have this, I can go back to this unique thing, right? Okay, I thought I erased this. All right, so I have all this. And so now YR is... Yeah, and YR is less than R. Okay, that was the proof I needed. So, and YR is less than R.ks length, which is this proof right here. And in fact, I can just replace this whole thing with HYR. And C is less than RK. So see, what is C? C is going to be, C is I over here. Because we have, on the right hand side, I'm rewriting this. So we have these two statements, and they're both about I times D. Okay. And here D is actually well here it is YQ, and here it is X times R dot D. And here, and A is Y, right? So Y is Y. So I believe both of these facts are true from things in this, and this is I dot prop. Let's see. Let's just see if I have this. So let's see if I have this in scope. So we'll say have equals by ASOP. But I'm already after the sorry, so let's move this down. Nope, didn't prove that. So let's get rid of that part and just have this. Ah, come on. That's how I defined it, right? Oh, no, I didn't. X times R dot D times R dot K. I feel like this should be proven. I don't. Okay. Let's define this as a constant. Let xrd is equal, or say set xrd is equal to x times r dot d, and then we'll say xrd here. Right, RFL, like, is that not the same thing? Not how it's defined? No, it's not how it's defined. This is the definition of no? Okay, I don't know why I couldn't handle that. I shouldn't need this, right? Like, I mean, it's not. Now it's by RFL, right? That's just the definition. By definition, that's what it is. Okay, so I don't think I need this for anything. Let's just leave it around as a thing that I might need in a second, but I don't think I need it right now. Okay. I don't even know if I need to do this. I think probably this is fine. But I just let's leave it. Okay. Okay, so this is defined. So now I have one of these defined this way, right? That y is equal to this, and then where's the other one? What did I do? Just do with the other one. Is this one? And then so now have hang on. Come on. We'll break it down again. Why don't we have this? This is the thing I'm trying to prove. And this is HYR now. Okay. Oh, it's M, not Y. Okay. Oh, okay. And we have this. So, okay, so we have... Maybe some of this was redundant. Okay. Should I even need this? Yes. Okay, so just to make this clean, I have this. So RKS get YR. I want to prove that these two statements are the same. So that I have two statements that are now the same, except this is the one I'm trying to prove. I'm trying to prove this one from this one by somehow unifying these two things. Yeah, I have this. This is equal to M, and this is equal to M. Right, this right here, RKS get I equals K. Right? And K is equal to this. Okay. I thought I had this. Maybe I don't have this. Did I just waste my time? I'm not sure. Is this not true? Okay. YR. No, this is not true. What I have is RKS YR plus RD times YQ is equal to M. So it's not this. This is some K, right? So RD, okay, so I have K. So RKS get, like Y. I want to give a name name to this. I'm going to call this like YK. So we'll say set YK is equal to r.ks.get of YR and HYR. Like I'm not seeing the path here. I think it's there, but I don't quite have it. And so now that we've set that, we can just call this YK. All right, so we have this statement, YK is plus RD times YQ equals M. I don't think this is going to give me what I want. But somehow I was able to show this is unique, right? That's the whole point of this, right? All right, so let's plug these things in. Have nat mod, nat div mod unique. What did we have? We had, well, we have it of, okay, so I need to take this yk and like obtain some other thing. So set, we'll call it ykr is equal to, we're going to set that to yk mod r.ks.length. I think that, okay, so now then we can plug in, we need to have, what do we need to have? We need, for mod unique, we have the this over this is this. We have that is yq, so a is, so we have y r.ks.length and yq. Why is it mad? Oh, I need this property first. No, what I need to do is I need to use this little @ sign so that it takes all the parameters. Wait, will it just infer that? Like it says these are like, what if I just put did I not have to do all this? It would say nat div mod unique. And the only thing I actually have to pass in is this parameter that says, oh yeah, and then I'm going to get this theorem back, right? So if I give it a theorem that says that something is less than the length of that, so I have yr is less than that, so yr. Oh, 0 is less than, I need something that's positive, right? So what is I is positive? No, but I want the length is positive. So that's r dot h size. And it's div underscore mod unique. R h size. And it does not know how to synthesize the implicit arguments. Okay. So those implicit arguments are y r.ks, no, sorry, r size, r h size, and then it's y r.k. I gotta do this. Ks. Sorry, I'm back. Huh? Because I put the @ sign, and then it has to go at the end. Okay. So it goes. Man, this is. All right. The C is y, and the D is the remainder, which is y. No, sorry, is yq. And this is not yq, h length. So C was y. Okay, so what? A is. Oh my god, this is annoying. So A over B, Y over RKS length. That's right. C is the mod, okay? C is what? The mod is Y remainder. And then D is Y. Okay, there we go. All of that gave me a theorem that this is all right. I need to stop and just okay. What is my argument? I'm just lost here now. I've completely just blown up my head here. My head has fallen apart. I'm gonna just put this up here so I can refer back to it, and you just say what you want to show. So it just makes it a little more readable. Right, so we're trying to show that. We know it's going to be hard because we have to calculate what this stuff is, right? We have to kind of reverse engineer everything. I said it was an attempt to force unification. So we simplify what this is, right? And at some point I said use y. Okay, so we have that. Now I'm going to leave this, I'm going to say x times RD. And R dot. So what am I doing here? Why did I do this step? I'm going to try and guess reverse engineer what n is. So we have I'm just kind of like filling in the docs to see like what these steps do, so that I can kind of read the argument. K, we're going to introduce some K that's a nat. Oh, I can't say that, can I? It doesn't let me say that. That's too bad. And then I'm just gonna rewrite this for so like I'm just assigning it to itself for documentation. Like rather than putting a comment here, I'm just gonna, you know, like this is basically functioning as a comment, so I can see what it is. All right, so X is the X lets us complete the equation. Right? What I'm trying to do, if I step back and think about it, what I'm trying to do is I'm trying to plug in a value for n. When I say use something, right, I want to plug in a value so that once I simplify n, like once I simplify n, I'll be able to show that these are the same, right? I haven't used this lemma up here, this thing, right? Because this gives me a bunch of definitions that I think are very similar. In fact, once I say use, like once I get rid of this n, then I can apply this term simp. So I'm going to press to do apply term simp to, so I'm calling it y, right? Like the, okay. And why did I do this at HK? Right now, let's hang on. What do we know about k? K is just an element. K is an arbitrary element of k is one of our constants. We know that k is one of our constants. We know that k is one of our constants. That's hk. And that it can be used for some x to produce m. See, the problem is you could have multiple ways of doing this, and maybe what I'm missing is because imagine that you have a rake, you have two arithmetic sequences, and they're the exact same line. Well, okay. Well, okay. So one is one of the terms in your one of the sequences in the rake is 0 plus 1n. So that's all the integers, all the natural numbers. Sorry. And then the other one is 1 plus 1n. That's all the natural numbers greater than 0. And then we can make this, right? We can say let def foo is going to be, it's a rake, and it's d is equal to 1, and ks is equal to 0 and 1. And then we can say, I keep doing this, I should probably make a function for it, but we can just say eval list dot range 10, and we're going to pipe it through dot map foo dot term. And so that's going to give us a 10. See, and so there's multiple numbers being fed into the rake that produce the same output. And I'm trying to reverse engineer the idea that I mean, I don't have to say that it's like this one, right? Wait. So I've proven it one way. So I've proven that if there's a term, all right. So what let me just. I'm just going to copy the exact thing that I've proven. I hit some weird button. Okay. All right, so I proved this. And now here I have to prove this, right? Which is just the opposite, this same statement going the other direction. So I've shown that if there's a term hang on. What did I do with it? Oh, here it is, right here. I was looking for this line. Okay, so this says if there's a term, then I've proven that there's some constant in here. So I've already proven that given this one, there's some constant that generated that one. Okay, fine. Now I'm trying to say if I'm trying to say that if I have one of these constants, and I can just make up a number, I mean, if I have one of these constants, I can make up some arbitrary x, multiply it by the constant, right? I have the k, some arbitrary k in my list. I have an arbitrary constant that I just make up out of nowhere, and that gives me m. And then I have to prove that there's an n that I can plug into the thing that gives me back that also gives me m, right? So there's a way to access that combination, and it's obvious to me what that is, but it's not easy to put into words. It's that right. The answer is use well, I have to know the index of k, so I have to know the I. All right, so k has some index. So let me rewrite this in English. In other words, given some k in our list and an arbitrary x, the rake will, the rake will we can the rake produces, the rake has some, we have to show that Okay, so given some k in our list and an arbitrary x, the rake ought to produce k plus x times rd at some point. We prove this by reverse engineering, by working backwards to calculate what n we have to plug in to produce m, so we'll call m at some point. We have to plug into r dot term into r dot term n in order to get n back out. Right? That's it. That's what I'm trying to say. Kind of a wordy thing. It's wordy even in the symbolic logic up here. That's complicated. Okay, but that's conceptually easy. Okay, so k has some. K is a member of ks, so it must have an index in ks, right? And we know that from a fact down here. Okay. So the formal statement is that k is equal to k dot r dot ks I, or it's dot get I, right? Okay. Which is this line right here. That's HIO. So what number do we plug in? The number has to be, n has to be some number, n has to be of the form n equals y plus x times, no, not even x, I times x times r dot d. No. M has to, no. Okay, so maybe this is fuzzy in my head. N mod r dot ks dot length. So I is this. Okay. we want to show this. And then x is equal to n divided by r.ks dollar. So what I need to take those two things and rewrite them in such a way. I need to solve for n basically. But I don't know is that what I want to show? So that k is equal to rs.ks n over r.ks.1. That's what I want to show. Not k plus is equal to m and is equal to this. Like KSI is equal to this nonsense. Like it's obvious to me that this is the truth. Okay, times r dot. This is how it's defined. It's how it works. So n over r dot ks. Hmm. See, here's the problem. And I've gone back and forth about defining things this way multiple times. K has no relationship to oh well, hang on. Shoot. See, I see what I'm doing wrong. Like, I I plugged this in I took a wrong turn here. Like, I used the denominator down here. Like when you plug this thing here, like the denominator is b, and I put in r.ks.length, and that was wrong because what I want to show has nothing to do with the length. I'm trying to. I want to talk about d. I want the denominator to be d. And what I want to do is I want to convert this somehow. Hey, do I? Hang on. Okay, it doesn't matter if it's unique or not. I just have to show that this is making my brain hurt. I have to show that this is the case. But how do I show that? Like they definitely have the same form. Well, okay, so basically I have to pick an n so that this holds. Not that I want to show that. We want to choose an n. We want to choose an n so that k is the constant that we pick, right? It gets that is so that r dot term n picks ksi, picks k equals ksi as the constant. That's what we want to do. So then I equals n over divided by ks length. Right. So we have to pick. All right, so this happens for any, for all n, such that right. Then we want to pick x. Well, x is, we have a choice between picking n or picking x, right? And I think x has to be this. I think this is right. But I think we have a choice about, but we have a choice about whether to pick x or n first. Whether to choose X or N first? Whether to introduce, or not introduce, whether to specialize, not specialize. Like we can calculate what X should be, or we can calculate what N should be. So we can either obtain X and calculate what N should be, or no, we can't do that. Cannot do that. I mean, that's the only thing we can do. Sorry. We can't do the other thing. We can't, there's no or. So we cannot. So we can't introduce N. We can't introduce an arbitrary M. We have to prove, right, so we have to show N exists. We have to pick K first, right? We have to pick. I'm sorry. We have to introduce. We also have some arbitrary X. Obtain. Not obtain. Yeah, but you obtain. Ah, yeah. See, I did cases. I was being stupid. This was stupid. I did this whole cases thing, right? What you do is obtain it. Obtain X. Like we have this as a fact. We don't have to specialize this. We can just obtain it. Ah. Why did I? Which is HX, right? HX 0. Now we can choose N so that as a constant. This was a. Why did I do this? Because I did it because I went looking for this thing. And I said this was weird, and what I should have done is obtain this, right? This should say obtain. Because this is different. This is like you know what x is, and you want to apply it in here. You want to remove this. But here you can remove it another way. When it's in the hypothesis, you can obtain it. Why didn't I remember that? Why I do it like 100 times. I did it like right here. Yeah, I did it right here. Why didn't I do it here? Because I'm an idiot. That's why. Okay. Okay. And let's say what the goal is. That serves. Right, so so in other words, K. Once we have so that K uniquely identifies a particular sequence within the rate, a particular arithmetic sequence within the rate. So x is the input. We have some arbitrary x that we feed into this sequence to get the result. And I'm going to put the right. It's not arbitrary. To get the result m. Okay. So then there exists some and we can obtain it. We can obtain it. Okay. And then now we choose n so that, right. Yeah, so we can't, and so then what does that mean? So we choose what? So then this unique thing should tell us what that is. So but it's not okay. This there should be some lemma that tells us what this is. I feel like this is this might be it, but I don't think this is quite it. I'm not sure that's quite what we're looking for. Look at my list of, I had a little scratch list here. So I said, that is scratch. Like every time I've tried to deal with this, one of these div mod situations, like every single time it's been a nightmare like this. You know, it's because you're dealing with this, like, well, it's an addition here, but you're kind of working backwards. And again, you know, it's not, it doesn't work the way rational numbers would work, right? Because you're in a very limited domain here. You've got integer division and you've got this subtraction thing, so that you can't reason about it the way you would if you had like the full you know, if you had like the real numbers or rational numbers or whatever. Excuse me, I'm getting tired. Well, okay, so in theory, if I, what I was thinking at one point, and I think maybe I've got it set up, I've got this cleared up. I don't even know what file I was looking at. This one. Not in here. We're in break, right? So we're going to say let n, we're going to define n now. So it would be I plus we need some little rule like this. It's like div mod add div. Do this. Okay. Oh, okay. So we need a rule here that says, I think I already have this h1 somewhere down here. Oh, the I prop, right? So we have I prop. So let have, so we have I divided by, sorry, I mod r dot ks length is equal to I, right? Rather, I is equal to, right? We want to go this way, so it becomes a substitution rule. So this is going to be hi1, right? Yeah, because we already have hi0. So hi1, and that is exact by exact but I won't be able to find it unless I do this. Have just introduce I.prop. And the prop, see, it's a fin, so it's the prop is that it's less than this. And then, yeah, there we go. So then immediately it found it. Once we introduce that, then it immediately finds this. And then we can take this out and put it back here. Okay. So now we can plug in, let this is i.r.ks.length. I'm sorry, imod. Like we're doing this a goofy way, so that it comes out right when we I'm gonna type a long expression into, right. I want it to match these rules, right? So I'm gonna feed in the exact thing that I need to do. Is x divided by r.ks.length. Use n, unfold, let, simple, and I bet this just works. It did not. Okay. Okay. No, that's not right. It doesn't just work, because first we have to do this. We have to unfold all that stuff, unfold all those definitions, and then we simplify it. Simple. No. Repeat simple. No, I didn't do anything. Ah, okay, now we have to, okay. We have this as a, see, we have this I. It's not simplifying this good enough. Well enough. No. What if we I.val do that? Is it? I feel like this should be. Wait, maybe I did this wrong. Wait, hang on a second. Oh yeah, I did this wrong. It's not. It's not this. It's x times this. There we go. Now it should simplify. Right. And can I desimp n? No. Because I think this is I times. Wait. N is. Look, I told the simp everything, but it didn't simplify this. It didn't simplify that to I. Right, so have n is equal to I plus x times rks length. I plus x times r dot ks dot length. I don't know why I didn't simplify that. Equals maybe can't. Yeah, that worked. Simple. Okay, so then rewrite this. I'm okay. I feel like I'm making progress here. I'm very close to having. So I have a definition of m here, and I have a definition of m. I want to prove this definition from this. So I think what I do is I rewrite this. Right? If I can write x in terms of this, n over. Right, so if I can say have x equals n over r, which I think by the rules of division this should be true. Have x is equal to. Wait, hang on. This. Like this would not be true for rational numbers, right? Because we're saying x. Right, so n is something plus this, right? But because the remainder gets removed, this is integer division. This is by omega, right? By omega. No, ASOP. I think this is true. Maybe it's not true. Simple. Okay. Great. How do we start this? We say, what do we know about x? Do we have a definition of x somewhere? That's here, but okay. So how can I rewrite? Like I believe this is true, but let me think. Right, because let me do the calculation that I want to do. Calc. We say n is equal to this. Right? Do we have a better definition of n? Oh, we have this right here. Okay, so we have this. I'm just, all right, so then have and I'm trying to get to this, right? But actually, can I just show that? Like, would that show? No. A plus X times RD. Like, I want to unify these two statements. So it would suffice to show this. So we can say suffices to show this by from by. The syntax is a little weird here. Right. So this introduced this goal, this right here. So we can say we can rewrite x here, simp hx. So rewrite hx, or rewrite this with at hx. And then simp all, right? I don't know why you can't just say by that. Can you say that? Right, okay. So because this is sufficient, right? So I provided a proof that this is sufficient. Now this becomes the goal. And then now we can prove this. And then how do we prove that? What? And this is all garbage I don't need anymore. And this is all garbage I don't need anymore. Right, all I have to do is show that these two numbers are equal. And why does it say okay, that works, and then sometimes first it works and then it doesn't work. All right, we'll say conv at hx, and we're going to rewrite, so convert at hx, and we're going to do like we're going to rewrite this. So we're going to use the rewrite rule there. That gives us this. Now we want to switch these two things. So I guess the whole thing is I have to say like left hand side. And now we're at an addition, so we got to go to the right-hand side. What? And then we have to apply nat mul com. There we go. And then switch it around, and then now we have an exact proof. And so all this can be on one line. It's just you can put it on one line when you're done, but when you're like doing it, it just screws up. This UI is a little clunky. Basically, you're navigating into this expression over here. So converting at hx, right? So when we start at hx, like before, we have this. We just have k plus x times rd equals m. But at the end of it, hx has changed into this, which is the exact same thing as the goal. And then so we say exact hx. So anyway, this is the proof that showing this is sufficient, right? All right. So then now this becomes our goal. Okay. How do I prove that? But what do I have about x? I don't have any definitions about x, do I? We have hx. All right, so if I rewrite k in terms of I'm not quite there. I'm not quite there. It's not x that I want. The reason it's not there, it's very close to this. I want something that looks exactly like this. And I'm going to use this this division thing, this lemma about division, that division, this div mod thing is unique. Or I'm going to use something very much like this. But I can't use this directly because k is not necessarily smaller than rd. In fact, in the sieve it's not. So the idea would be, well, okay. So again, going back to the example, right? Here we would say 2 equals the delta is 2, and then you have 3 and 5, right? And then you get these, and well, it's not that. I know what it is. It's 6. What you do is you say, right? So you, what? Okay, that crashed. When I do my sieving operation, right? In fact, this is what greater than and equal does. Is it? Well, I mean, like the. Okay, so these are all the natural numbers. Right, right, right. So I've started with d equals 2, and I've interleaved the evens and the odds. Okay, so I have two sequences, and we're rotating between them, okay? Right, that makes sense. But then when I so I have all the natural numbers. I want to remove all the even ones, and now I have all the odd numbers, right? So I removed the 0 term. Now I have all the odd numbers. And then the next step that I'm going to do, like how this rake works, or how the sieve works. Okay, so I've got the odd numbers, and now I want to get 3 and 5. But I've got this 1 here, right? So I'm going to increase this to 3, right? And that dropped the 1. And so now the 3 is greater than the 2. And so all the odd numbers that I'm interested in are that. And if I don't do that, then at the next step, I have this 6, and it winds up being 1 and 5. And you'll see that when I go to the next line, I have all the, these are all prime, except for 25, these are all prime numbers. But I have this 1 in here. And in order to get rid of that 1, what I do is I take this out and put a 7 in there, right? I just add it to the 6. I add the 1 to the 6, and now I change that, so I just fast forward that one sequence. And now we have 5, 7, right? So now the 5 comes first, and then instead of I just dropped the 1 by doing a little leapfrog operation. The 1 moved over here. If I put the 1 back, you get 2 copies of the 7, 2 copies of the 13, 2 copies of the 19, and so on. So they're generating the same sequence. That what I just showing you is that the 1 and the 7 are both the same sequence, but they're shifted, right? So 1 plus 6n is the same as 7 plus 6n, except the 7 plus 6n has dropped the first term, right? They're the same line, but shifted above. Right, like we literally, like if you draw the line, right, you literally shifted the y-intercept or the x-intercept up. Okay, right, so that's that. I'm gonna take this out. Oh, maybe I'll leave it in here for just a little bit. Maybe I'll put it right at the bottom so I remember to take it out. Put it right after this proof. Okay, so that's my problem. So in order to combat that, what I need to do is instead of x, and instead of using hang on. I need to do something like that. So the situation is, it's possible now. All right. Okay. So here's the situation. Like, say m is 13, or let's put it back the other way. So we had 1 and 7, right? M is 13. So it's generated by either the 1 or the 7. And I've arbitrarily picked one of them, right? So I picked one of those to be my k. Oh, I see. Okay, so it's more like one of these is the case. Like there wouldn't be two of these in here. There's either one or a 7 in here. Um, it doesn't matter which one it is, right? But if it's the 7, if it happens to be the 7, like this is a perfectly valid rake to have. So it's entirely possible to have this situation. It won't happen in the sieve, but just the rake itself does not know that this is not gonna arise in practice, because it can arise just by doing it, right? Like I did it here. So in order to prove that these two things are equal, in order to use this fact that the thing is unique, I can't, I have to disambiguate between these two, and it doesn't matter which one I have, but I have to say if k right. So I have to say I'm going to make I'm going to say k1, let k1 how about k prime? K prime is equal to, I think I have to do it like this. If k is less than r dot d, then k, else k mod r dot d, right? Right. And let x prime equals, if k is less than r dot d, then x, else x plus r dot d minus k mod r dot d, right? But there's a slight catch. If k is greater than r dot d, so compensate. I'm doing the right thing. I'm not sure I'm doing it in the right place. Let me see if this. Let's see. So I want to plug that in. Let me just double check that this is the same. Have k plus x. Have k plus x times r dot d is equal to, call a sanity check. Is equal to k prime plus x prime times r dot d equal to omega by ESA. So it solved one of them. And then we do, so it solved the positive case, and then the negative case, does not solve it. We've already simplified everything. Is it ESOP or ASOP? I don't know. I guess it's. How about we say dsim k prime and x prime? How do you get rid of this? Oh, okay, we'll say have. Come on. We have to show this. Oh, I did the wrong thing. Instead of saying less than, I should have said less than or equal to. So now, oh. No, I didn't. I did the right thing. Oh, I was okay. So I got this. This is looking back. So have hk prime is that k is equal to this. That k prime is equal to that by simple. Stop. Have hx prime that x prime is. I'm just like filling in this if then, right? I don't know how to remove that. because they're defined like that over here. And so I'm going to simplify that. I don't know what to do to make this simplify by on its own. Dsimp at K, maybe dsimp at X. Well, it did that, but it didn't dsimp H at X. Simp H. Yeah, it's not. I'm not sure what you do to eliminate this thing, so I'm just rewriting the else part for each one. So X plus RD minus K E by ESOP plus R dot D. This is just a sanity check, right? Even the sanity check takes 10 minutes, 20 minutes, an hour. 4:30 in the morning. The skills, right? My skills are not up to. All right, so now we can simp all. There we go. And then maybe ESOP can solve it. Nope. Right. This is the exact problem. Like I'm expecting RD to simplify here, but it doesn't. Right. Did I do the right thing here? Let me just double check this before I try and prove it. Right. What am I trying to say? All of this was true. Let me put like a little headline saying what that little comment saying what this thing was doing, because I gotta remember. So what is this all doing? So we're trying to say that from this point down to here, all right, so plug in into the formula and simplify. Hang on. I did this wrong. If I had put this here, val ks.length, or actually I can just say dsimp n. No, not dsimp. Unfold let n. No. So okay, hang on. I get this. This is what comes out. This unfolding is doing nothing right now. But if I move it past here, no. This worked a second ago, right? Oh, because I just rewrote this, right? Hang on, let me just undo it so I get it back exactly how it was. Yeah, I rewrote that. But what if now that I've simplified it this way, I rewrote it that way, what if I rewrite it with this? In other words, this is exactly the same. Or I could rewrite it with hi1, right? Instead of doing this, rewrite with, let me just comment that out later. Rewrite with the reverse of hi1. Right, so what that did was that changed this. And now I have two of these things. And I think it's going to simplify better. Did it? Like I want to distribute this division, but I don't think it works. I don't think you can like nat div dist. You can't. Div sum, div add. It's more like adding a add mod add div. Like div. Which is what I'm looking at, right? It was already on the screen, right? Would it not be the case in have I mod r dot ks dot length plus and divide the entire thing by r dot ks dot length, I would expect this to simplify to x. I would say have this by what? Sorry. Right? Because like this is the remainder. That's how integer division works. So this part gets canceled out. Right? So it would be called nat mod add div. I keep coming as it's the last thing I just no, it's mod add mul. Right? More like add mul div or something like that. Yes, this add all div right. So simp at nat add mul div right. It's not simp. What do I put it in? I have to show that 0 is less than z, which is what? r.k. So we have, which is I have, which is r.h size. So what do I do here? So I have this form, so I can rewrite it with r.h size. I have to pass that in. Oh, come on. I have to give it to x and the y. Okay, so the x is I dot set I prime is equal to I dot val mod r dot ks dot length. Oh, actually, this is fine. Okay, so this right here. We can skip all this stuff. We can just go right here. We have this up here. So we have to give it I dot val and r dot ks dot length. What? X, y. Well, we have to give it y. Okay, so x. Give that. There we go. Now we've gotten still have this. So we can rewrite and so now we have like mod div should be 0, something about 0. Mod div 0 or 0 mod div self. What's this? Yeah, yeah, this is what I'm looking for. Nat mod div self. So if we simplify this with, all right, so we can rewrite, that's the reverse of this. So hi1, so we write left hi1. No. Oh, not the reverse of it, just hi1. Say simp hi1. Wait, what's the matter? Why is it no? hi1 right there. hi1 says that this. Oh, I see. Yeah, so we want to rewrite it with the left of that. There we go. Okay, so now we have this. And then if we simplify with that, that was marked as a, yeah, see, this was marked as a simplify rule. And look at that. That's exactly hx except for, yeah, so we can apply nat mul is commutative mulcom. Nope. Oh, we have to rewrite that. There we go. And that's exactly it. All right, so then we can probably put these all together into one rewrite sequence. Yeah. Yeah. Simp. And then it's exactly hx. Exact hx. No goals. And all this stuff is garbage. Okay. Well, that's proven stuff in Lean. And so now we use this. Now we run this definition through the formula. We not through through r.term n. This definition of n through and once we simplify, once we deal with annoying div mod issues, out comes the result. I'm just kind of golfing now, see if I can. Nope, doesn't work. So not really golfing, just removing white space. Right. Yeah, like it doesn't really matter what these lines are. Like the logic is there. It doesn't. I don't see that formatting these lines gives you any insight into what it's doing. You just, this is more of like a comment, right? In this particular case, the actual comments are the real, you know, the more meaningful proof as far as I'm concerned. Okay. I have no idea what the top thing means, right? I bet I can just drop this. Yeah. Like that's a speed up. But I think this was a ESOP generator proof, right? So I don't really know what this is. But, you know, I'll just put a little comment here and then I'll be done. What does it say? It's pretty easy. This I'll make it look like a little bit more of a structured proof. That and then once we simplify these face off. This is basically this is just front work, but it follows from the definition of term. Okay, that's good enough. Good enough to say that. Yeah. I don't even know. I did not expect that to take 5 hours, but like, you know, you don't. It's a search, right? Like, you know, it's mathematics. It's a proof is a search. Like you have to find a path through the woods. It's not just like tell the computer what to do. You have, you know, the whole reason Lean works is because programming and proving are the same thing, or at least they're made of the same stuff, but they're not the same mental activity. Programming, you want to just tell the computer what to do and you do it and it's easy. At least for me, I've been doing it for 30 years. This just not easy. But you know, I wish programming had this over here, like had the goal driven stuff. And I think it could, because a lot of times, like, I mean, you know, I've had many live streams on here, but I don't usually stay up till 5 o'clock in the morning. And I've done a lot of live streams where I stayed up to 5 o'clock in the morning since I started doing Lean. And it's because you get this feedback loop, right? It's you know, it's not just a compiler giving you feedback on what you've done. I mean, there is that, but it's also giving you goals and progress and so on, and you're seeing it in real time. And it's just very, like, I had fun doing this, right? Like it was painful and it took way too long, but I enjoy this, and I wish that I had this kind of mental engagement in regular programming. You know, like with this, you set a goal, and then that goal was up to you. You stated something, and then it looks at what you stated and breaks it apart into pieces and says what you need to do next. And I think, like, if you're doing any kind of top-down programming, that same kind of thing could be applied, right? I did a whole video about like my dream REPL one time. I think maybe on my other channel. And I call this like the stack-wise refinement. So it's stepwise refinement where we start with a goal, but you include not a theorem prover, but a goal-directed search in the computer telling you what to do. And theorem provers have this. And I think that you could make a case that regular programming could have this. And if I had an IDE that did this for regular programming, I mean, Lean does it now. But it does it for the proof side and not like it doesn't automatically do it for the programming side. And I wonder if there's a way to make it do this for the programming side, right? Where you kind of specify what you want the program to be. I mean, in a way, that's what I'm doing now. Like you know, a little bit. It's like I specified what I wanted a prime sieve to be, and then I built rake sieve so that it fulfilled that promise and like talked to that. And then I built rake to do that. So it's like I'm kind of doing that, but it's being like again, I don't feel like what I'm doing right now is programming. Like the algorithm was written in a few minutes, right? So I'm talking about using this kind of goal-directed search for like bigger projects where I'm just doing programming and not necessarily trying to prove the correctness of it. But I don't know. It's just something I've been thinking a lot about. Like, I mean, I wanted that for a long time, but like using it in Lean, like it just demonstrates how much to me how engaging this kind of interaction is. And if I could do this for a regular programming language rather than just proving, then it wouldn't be so hard for me to prove things, right? I mean, it wouldn't be some like programming is much easier, but if I had the thing that's easy for me to do plus this interaction like driving my brain, I think I would be far more like I would be incredibly productive. And not get distracted as I am wont to do. Anyway, yeah, this was a gamble here. So this was my hope is that by doing this again, that the 5 hours I spent here saved me 5 hours on each one of these. I don't know if that's going to be the case. There's no way I'll ever know that that's going to be the case. I guess if I find out that this theorem is useless and I never use it for any of them, then I know I will have wasted 5 hours. But on the other hand, I had a good time and I got a video out of it. And I mean, not that anyone's gonna sit here. I mean, I guess some people are watching. If anyone is watching 5 hours of this video, thank you very much. I appreciate it. I hope you had the sense to speed it up. But, yeah, or at least I don't know. Whatever. Thank you for watching. And yeah, I will, I guess, be back and do. With any luck, these will be a little easier. 1, 2, 3, 4, 5, 6, 7. Probably not though. Plus, I gotta fix these. That should be easy. All right. Well, best of luck. See you later. Oh, I didn't even record this. Wow, I'm so stupid. YouTube recorded it, so. All right. Adios. Thanks for watching, and I'll see you again soon.